constantly pulling down on the satellite, preventing it from moving, but it's weak enough so that it stays in space and it's like not pulling it down directly.
That's exactly right. If the Earth's gravity had been too much for this satellite, it would come crashing into the surface, right? Yeah. If Earth's gravity had been too little, it would go creaming off into space. But we found a way to put like thrusters, which are just little engines, on satellites to keep them at a certain velocity that will keep them perfectly in orbit. So what's happening really is this is staying in orbit due to centripetal motion, what we talked about with the cup in the water. So the Earth is pulling, again, the force of gravity, the force of gravity is pulling this satellite toward the center of the Earth every time it moves. When the satellite's here, it pulls it in here. When the satellite's here, it pulls it in there. So it's constantly pulling it toward the center. So the force of gravity is what was really supplying your centripetal force here. Remember, we said that, I see both your hands. We said when we see a car in circular motion, friction is keeping it there. When an electron is in motion, the nuclear force is keeping it there. So this case, the force of gravity is keeping the satellite in orbit. Danae, and then the guys in the back.
So you said they have thrusters on it, right? The thrusters just, are they constantly going?
They're going it whenever they need to go. So for example, imagine there's some sort of a satellite is not in the Earth's atmosphere, it's above the atmosphere.
Right.
So it doesn't have to worry about air resistance because it's in a vacuum, it's in space. So there's no air resistance.
Right.
So it keeps it at a constant motion. So it might be constantly firing at a certain rate so that it keeps moving around the sun. We're going to do an example today where we can figure out exactly what might that height be. So if we can figure out the height, we can figure out the exact balance to keep it there. If it's at a certain height, it will work perfectly. If it's too low, it'll come crashing. If it's too high, it'll go off in space.
So what do they do like when it runs out of?
Oh no, the thrusters are what get it going. Once it gets going, they turn off and then it continues to orbit based on the height it's at.
Okay.
Okay? They don't just keep running and the juice runs out after a while, no. They use the thrusters to shoot it out into space. They get it going at a certain speed. They turn the thrusters off, and if it's at the exact perfect height, it will stay in motion forever.
Okay.
That's all it is. And we're going to determine today what that height is. Okay? Good question, guys.
But then I had a question. So how come the satellite has no chance of being pulled by the atmosphere?
The Earth's atmosphere is not pulling on it. The atmosphere, you're in the atmosphere now. The atmosphere provides air resistance. Once it escapes the atmosphere has no effect on it. It's not like pulling it back in. The Earth's gravity is pulling it, which keeps it in orbit, but it's not pulling it into the atmosphere. Okay? Atmosphere is more of an air resistance term you can use for that. Okay, not gravity. There's no gravity effect there. Number 2. Is there a gravitational force between two students sitting in a classroom? If so, explain why you don't observe the effects.
Because we are blind.
It's too weak. It's so insignificant. It is so insignificant. And what I want to do today, we're going to answer these two questions here with example problems. That's one of our goals for today. Again, to be able to answer these problems here with examples. But we didn't actually go through the example of something like two students. We did 2 billiard balls. Remember billiard balls?
Yeah.
Yesterday? Or 2 pool balls?
Yeah.
And the force between them was so minuscule that they're not actually being pulled toward each other.
20-something.
Okay, they're not actually. I understand. Just move back here. Move on. For this kind of a problem, guys, you can think of 2 students, 2 calculators, 2 pens, 2 markers, whatever it may be. But anything on Earth that is pulling at each other has no significance because the Earth is so much bigger. The Earth's gravitational force overcomes whatever we can provide. Okay?
I thought it was just in waves. That's why we couldn't see it.
No. I mean, sure, physically you can't see it, but you can't see its effects because it's so minuscule. You can't see anything because they're all in waves. Even the force of gravity from the Earth pulling me down, we can't see it. We can see the effect it has on me. It holds me down here, right? I jump, it pulls me back down. That's the effect it has. You can't see the effect between Karen and Star pulling on each other right now, even though they're not look like they're pulling on each other. They are. You can't see the effect. No matter what, you can't see gravity because they are waves. Yes, you can think of that. Number 3.
the Earth is gravity stronger, that's why.
If you had two objects in space and they were literally just sitting there, they would begin to start orbiting each other over time, because one of them would be bigger than the other. So the bigger object would be in the center, the smaller object would begin to orbit. Why isn't this pencil orbiting? You know what? Let me give you a good example. Here's a video.
Water?
Oh, wait, is that the video you were talking about?
I know, I feel like deja vu right now. Hey, you guys have the video up, right?
Oh yeah, I've seen this.
You're an insight student.
Oh.
Can you hear me now?
Just go to YouTube.
Oh yeah, I remember that.
You're so fast.
Aww.
Somebody got reported.
Yeah, there's no like fact.
Oh, that's recording of a recording.
I know.
Oh, they got cheat tape.
What, you just saw that? You mean?
No, yeah. 'Cause I was asking
Sure.
about-
It does, but the fact is that the pull between two people is so insignificant gravitationally that you don't see it. But really, there is a pull between any two objects. I mean, a piece of paper has a pull. Here, we're trying to joke that Peter got so big that his pull is so large that you actually see it. Not really gonna happen, okay? All right. So, the idea for number 2,
Record.
I just started, thank you. The idea for number 2 again is that we don't actually see it. Number 3 was a good problem, but here's what I want to do. I'm not going to give you the answer. I'm going to go through how you would do it, and if you had trouble, I want you to continue this weekend.
I was too lazy.
Okay? I'm going to go through how to do it. So, the Earth has a certain mass and a radius. Saturn has a mass and a radius. Relax, guys, relax. Listen up here, please. Find the weight of a 65 kilogram person at several locations. Here's what you need to think about. Here's the Earth. Here's the center of the Earth. Here's a person. Okay? There's a person. So the distance between the center of the Earth and the person is just whatever the radius of the Earth is. Again, so for part A, you're going to use F, as always, G, M1, M2 over R squared. Now, R in this case, for part A, is just whatever the radius of the Earth is. But now imagine that instead of a person there, you've got a person standing on the top of a mountain. So this is now, let me say a hill, not a mountain, because that's not going to look clear. So there's a hill there on the Earth, and now the person is standing on top of the hill. Okay? So now, they are not only a distance of the radius away, but whatever this additional height is right here, that's how far they really are apart. So for part A, you're going to use this right here. For part B, you're going to use, yes, F equals G, M1, M2, but now the radius is not the radius of the Earth, but it's the radius of the Earth plus the 1,000 kilometers. Again, this is what you want to think about here. For the first example, the person and the center of the Earth are a distance apart of whatever the radius is. But now take a look what happens. I'm walking around, okay, I happen to be hiking up a mountain, so now I've climbed all this height, 1,000 kilometers. So now I'm not a distance apart of whatever the radius is, but the radius plus this other height. So my distance is RE, which is the radius of the Earth, plus the 1,000. Again, RE is the radius of the Earth. And that's what's given to you in the problem here. So when you solve this problem, you're given the radius of the Earth. The radius is 6.38 times 10 to the 6 meters. This is in kilometers. So you should probably convert your kilometers to meters. Okay, so here, when you do this later on, the radius of the Earth carries down, but this you can write as 1,000 times 10 to the 3rd meters. Okay, when you're converting to meters, kilometer means 1,000, so times 10 to the 3rd is 1,000. Again, so convert that to meters. If you're still having trouble, you got to come in and see me. I'm not going to stop the conversions now. That's your conversion. So again, remember the only difference here is this. The mass of the Earth is the same. The mass of the person is the same. G is a constant throughout the galaxy. It does not matter. G is the same no matter where you are. Here, this is not G like 9.81, remember. This is 6.67 times 10 to the negative 11. It is a universal constant. Now, Here, though, the denominator was just the radius squared. But now you got to take the radius, add on the 1,000 kilometers, and then square it. Because you're not only a certain distance away, now you've climbed a hill. The same thing goes for parts C and D for Saturn. Only thing that's going to change there is you're going to use the radius of Saturn, and you're going to use the mass of Saturn. Radius and mass of Saturn. Okay, if you had trouble on the third one, please go back and try it again. Please go back and try it again. Here's what I want to continue with now. Okay, let's start with something where we're going to prove the value of G, and we're going to prove the value of little g, which as we know is about 9.81. That's what we're going to start with. Okay, what we're going to do is this. We're going to use our formula FG M1 M2 over R squared to show where 9.81 comes from. Because this number is not random. This number is based on the formula F equals GM1 M2 over R squared. Okay? So let's start. Let's say to ourselves for a second we have F equals GM1 M2 over R squared. Now, this force is the force of gravitation. So it's the same thing as your weight. Okay? Again, just like yesterday we talked about this, or 2 days ago, it's the same thing as your weight. So, taking a look here, these two equations are really identical. And we proved that the other day. We showed real quick where we found the person's weight, and then we did all this math. They came out to be the same number. You were supposed to finish out this number at home. But they come out to be the exact same number. Now, this says M here. What is this the mass of really, though? The person. So, if I want to call this person, what could I call it? P. Okay? Fair enough. Now, we are determining the value of G on Earth, right? This is 9.81. That's on Earth only. So what is this the radius of then?
The Earth.
The Earth. Again, the distance between the person and the Earth. So if I called one of my masses P, I can call that P now, and I could call this E. Again, P is the mass of the person, E is the mass of the Earth. Again, we are trying to figure out the force of gravity on a person by the Earth. So we have one equation on the left, we have one equation on the left, we have one equation on the right. Okay? They are both equal to the same thing, so we need to go ahead and set them equal. Set these two equal here. So take this one, set it equal to this one now. What do you notice on both sides? MP, so what do we do to them? Good, because they're in both numerators. Cancel MP with MP. So what does G turn out to be, guys? G ME over RE squared. Well, take a look. Aren't these all constants?
Yeah.
The mass of the Earth is a number. The radius of the Earth is a number. G is a value. It's a universal constant. If you multiply these three, you get 9.81. Go ahead and try it if you would like. We're not going to go through the math right now. But if you take G, which is 6.67 times 10 to the negative 11, you take the mass of the Earth, which in this case, mass of the Earth, in case you're wondering, it's in your book if you want to look, but 5.9 times 10 to the 24 kilograms. The radius of the Earth is 6.4 times 10 to the 6 meters. If you plug in the radius down here, plug in the mass right here, plug in the gravitational constant G, which is 6.67 times 10 to the negative 11. This is units of newtons per, or newtons over meters squared, kg. Oops. Okay, that was from yesterday. So using those three numbers, if you plug them in here, you're welcome to check. You'll get approximately 9.81. Again, approximately, because we did round some things here. Remember, when you square the radius of the Earth in the bottom there, you got to square that whole thing. So when you plug in 6.4 times 10 to the 6 in your denominator, you got to put parentheses around it and make sure you square it. Your numerator, you need to multiply these two. Put parentheses around the expressions. Use that big E thing, and second EE to bring up your exponent. So in your calculator, it looks like this. Oops. That's right. Okay? Again, that's what you should be doing. This is your numerator with parentheses around the whole numerator. Then press divide, parentheses around your denominator, and make sure you square the denominator. Okay? If you want to be safe, doesn't really matter right now, but to be safe, you could put another set of parentheses around here to indicate that that's a denominator as itself. Okay? Elizabeth. And this will give you, sorry?
That's a negative sign, right? For the-
Negative 11, yeah, because it's 10 to the negative 11. Okay? What will this give you? This will give you 9.81. Okay, you might get like 9.809 or 808 or something, but approximately 9.81. The same thing is done for everything else, guys. The mass of the moon, the radius of the moon. If you have the mass of the moon, put the moon here. Again, put the moon right here. Put the radius of the moon here. Use the same G, and you'll get the gravity on the moon, which is around 1.6. How did they find what? Which part?
But how did you get the answer?
I don't know.
They put it on a scale.
The radius and stuff is all trigonometry and looking at angles. You can always determine that kind of stuff. I can spend a day, maybe one day, showing you how to do it, but it takes a while. The mass of the Earth is taking a sample and extrapolating. So taking a sample of the Earth and estimating what it is. No. No, the mass of the Earth that is listed always is the actual mass of the Earth without like people and buildings and stuff. Okay? Sure, it does accumulate more, but we are actually so insignificant. The core of the Earth is so dense that a lot of the mass comes from the core. And then some of the mass comes from the layers, and then very little of the mass actually comes from the mantle. So by looking, they send sonar waves into the Earth, and by the rate at which they're reacted, or by the rate at which they come back, they can test the density of each layer. Knowing the density and the volume, you can find the mass of each layer. Knowing the mass of every layer, you sum those up to get the mass of the Earth. So they're using the density of the different layers. Remember, the core is very dense, so the waves come back at different angles. Based on the way the waves come back, they can determine the density. How about G? Where did G come from? I don't know. I can look that one up and get back to you. I'm not sure about G. It's a good question. Big G, not little g. Little g we just showed. I would put it in brackets to be safe, but you should get the same answer either way.
I got it.
9 point what? 6 and something?
Yeah.
Again, guys, it's an estimation, guys. These decimals go on for like 20 more digits because we're rounding here. So there's going to be a lot of error in your estimation, but it's a general idea of where it comes from. Okay. Let's quickly talk about tides so we understand conceptually what's going on with gravity here. So let's say we have a dock and there's a boat and it's sitting in the water. So let's say the water level is here.
Sitting in the tub.
Okay, the boat, there's a dock, there's the post in the dock, it's roped in. Okay, so the boat is attached to the dock, the person has docked it on the shore, there's some water there. This is like a pier, and then this is the land right here. The land goes into the pier, and then the land goes down like that. Okay, so this is like the back of somebody's house, they always have docks in the back. Okay, so there's a house over here on this side. So anyway, you have a boat sitting on the dock. Okay, so it's sitting on the dock there, say on the dock meaning next to it. It's been attached to it so it's not going to move. Now, the problem is this. We have to think to ourselves, well, what happens when the moon is not necessarily at the same distance from us? So for example, The Earth is constantly revolving. The Earth is constantly revolving. It is also rotating around the sun. The moon is rotating. Okay, it's also revolving around the Earth. So based on where we are today, for example, let's say here's the Earth and here's us in New York, or DC. Sorry, from New York. So here's us in DC. So imagine the moon happens to be here tonight. Okay, imagine the moon happens to be there. But you know what? The next night, or 24 hours or 12 hours later, example, we are now on the other side of the Earth. So now the Earth is rotated like this. So now we're on this side of the Earth. But the moon hasn't moved as much. 12 hours. The moon hasn't moved as much. I corrected myself. The moon has not moved as much, so maybe now the moon is down here. Okay? But this is not geometrically correct.
So the moon moves?
Okay?
I thought we only don't.
We move around the sun. We also rotate. The moon also rotates around us. Okay? The moon is a satellite. Satellites rotate about an object. The satellite, the moon, is rotating around
So
us.
it's like spinning
Okay?
teacups.
So yes, that's exactly what it's like. That's a good analogy I can use. Thank you. You go to any sort of theme park. You get the spinning teacups. The teacups are rotating, but then the teacups themselves are also spinning on the saucers, right? So you have the thing spinning within something else spinning. That's what's happening here. So throughout the day, the distance between the moon and the Earth changes. Now, the moon's gravity affects the Earth. Now, the Earth clearly affects the moon more because the moon is revolving around it. But the moon affects the Earth with tides. So when the moon is closer here, this might be the situation. But when the moon is further, what happens to the water level?
It drops.
When two objects are further apart, we talked about this on Tuesday. When two objects are further apart, their gravitational force goes down because the distance between them is going up. And the distance, r, is in the denominator. So remember, if things are closer, they have more pull. If things are further, the pull diminishes. So as the moon is different distance from us, the pull between the moon and the Earth will change. So the water level will rise at different levels. So they're able to predict this. If you open the newspaper, forget the newspaper, let's use Google because we have it.
Yeah, they're like certain times of the year. It's like five times bigger.
Okay, let's take a look now. Today?
When the sun is further,
This way.
the moon is further away, the water decreases.
Correct, because there's less pull. So take a look here. You have high tide, which is about 6 1/4 feet above sea level. Then low tide actually drops below sea level. And what's the time gap there? About 6 hours? Okay? So what we can see is that we're on like a 4-time-a-day cycle. There's 2 low tides and 2 high tides every day. 2 low tides, 2 high tides, based on the fact that the Earth is rotating and the moon is revolving. So we pass the moon twice every 24 hours. When we pass the moon, we're at high tide. So again, this is when the moon is closest to us. So that's when DC lines up with the moon. When DC and the moon are opposite, when the moon is on one side of the planet and DC is on the other side of the planet, this is when you have the low tides there. It happens twice every day.
So, you know how sometimes early morning, like, what's it? It's like,
The moon is always visible if it's in the sky. It's just that during the day, the sun blocks it out.
so
Actually.
yeah.
The sunlight takes over the moon. That's why you can't see the moon. But sometimes you actually can't see the moon at all. And that has to do with the waning, waxing, and all that stuff. Yeah, that's on a 27-day cycle.
Like a shadow.
Okay?
It's like the
It's a shadow of something.
Shadows
Yeah.
and it has, so the surfers
Oh,
go
yeah.
surfing on high tide.
Do surfers go surfing on high tide? Surfers look for higher waves. Tide is not the same thing. Remember, guys, waves are not caused really by the tides. Tides are the water level going up and down. The waves is more of the friction as the water rushes to the shore.
Isn't it better if
It's better in like storms. It's the same amount of water, Elizabeth. It's just this, guys. Here's what's happening. Sorry,
Oh yeah, where does?
guys. Water's conserved, so the water's not going anywhere when it goes down. Here's what's happening. Here's the Earth.
Yes, we recycle water.
The moon is over here. So all the water that's going down over here is getting pulled up over here. So the earth starts to kind of like stretch a little bit. So all this water, okay, over here it's high tide, over here it's low tide. So the low tide, all that water that you lose is kind of getting wrapped onto this side of the earth. Again, wherever the moon is, the water is being pulled to that side of the earth. So you have high tide over here. But later on in the day, when the moon is over here, now all the water is getting pulled this way. So you have high tide. So what do you have over here? Low tide.
So when
It's just opposite sides. So one side is high tide, one side is low tide.
So it doesn't.
Okay? Jason, it could be opposite.
Oh my gosh.
So what if we don't have a moon?
If we didn't have a moon, we would not have tides. We would not have tides at all. The water level would be at a consistent average, whatever it may be. So the water level would be at 3 feet in this case, at all times. It would just be pretty much, yeah. It would still have waves, but the water would not be moving up and down throughout the day. Have you ever gone to the beach, and in the morning, you're sitting up by the water, and then suddenly, throughout the day, the water's creeping up, and like suddenly, where'd the water come from? It's right next to me. Well, 6 hours might have gone by. And after 6 hours, now it's at high tide. Okay? Then it goes back to low tide. Why does it smell? Why does it smell at low tide?
It
It smells. Oh, yeah. Like at low tide.
All the bottom.
Sure, the fish, all the what? All the bottom's left behind. That's what it really is. It's the fish and the stuff, but it's left behind. When the water comes up to high tide, and then later it goes back to low tide, it leaves behind all this residue. Seaweed, little crabs on the water, all the stinky stuff. That's why at low tide, it smells. Now, here's another fun fact for you. Here's a fun fact.
Fun.
Here's a saying. Let's see who knows their stuff.
Happy as
Anybody hear that saying before?
Yeah.
Happy as a clam?
that one is thinking open.
Guys, up here. Happy as a clam. Raise your hand if you've heard the saying, just if you've heard the saying. Okay. Does anybody actually know, not computer guys back there that can look it up, where does the etymology of this saying come from? Where does the etymology? Tasir? Okay, China? I have no idea of country, but where does it come from? As in physically, where does it come from?
Me? It came from the clams who were happy to get out of the water because they was left behind.
Opposite. Okay, so here's the real saying. Here's the real saying. Everybody ignores the rest of the saying. The rest of the saying is at high tide. It has been abbreviated to say happy as a clam. This is the real saying. Because at high tide, all those clams that would be exposed at low tide are now covered up by the water. When it's low tide, there's a lot of clams left on the shore, and they're very vulnerable to being picked up by people and being eaten, or animals, whatever. But at high tide, all those clams that would be exposed are now covered by the water. So a clam is happy at high tide. Okay, this is the real saying. It's been abbreviated to be this.
Have you ever had
Like on SpongeBob.
Okay.
I don't eat any of this.
Mr. House, the clam buy them.
I do like that.
But are they the same? It's their mouth.
Yes. When we're by the moon at high tide, on the opposite side is low tide.
Are they the same as oysters?
They're shells, so they're not the
Like, you
same
know,
now.
when they open up and they cut the little
Yeah, they still pop them out, eat them and stuff, yeah. But clams, traditionally, you cook. You could eat raw clams, for a lot of people you cook. You know, you get like steamed oysters or fried clams.
I told you.
Yeah, I mean, usually you fry it, or a lot of people do like to eat it raw. They take a pot and knife, put it out. I don't like raw stuff, so it wouldn't work for me.
I don't like it.
I do like sushi. That's
Okay. Okay, take some time.
That was like for a year.
I can eat fried oysters. I can't. I don't like it.
And Victor was like,
Except ice cream. I hate fried ice cream.
Fried butter.
I need fried butter.
Look, I don't go to those kind of.
Please, go ahead, try number 3. Number 3, number 3.
The final page.
You work with a partner or work on your own, either way, as long as you're doing this work. Try number 3, number 3. Okay, it's not the homework, it's something I want you to do now. I want you to notice and look at your answers. Now, this is,
What page?
it's page 242.
I know.
I'm adding a part D to it.
No, why? If he wants to. If it's out, and after the, okay, I get it.
Okay? Part 3 is really not difficult at all. Or the part D is not hard. Okay, again, please try this. Please try this. Why do your answers make sense at the end? So you have a lot to do here. Get your calculators out. You're going to need to use scientific notation. Remember, you need scientific notation. You have to write down G. If you forget what G is. Remember 667 always. 667, negative 11. 667, negative 11.
7-11.
667, negative 11. That's what I always think in my head. Okay? 667, negative 11. Okay, come up with, guys, any sort of
7-11 minus.
trigger will help.
No, it was something else, like 8-11. It was still the math.
Okay, NF squared over kg squared in units. 667, negative 11.
Why do your answers make sense?
Why wouldn't I get a D back?
They are all to the 6th power.
I'm going to pause this while you guys are working so we don't waste.
Hi, back.